Hello everyone. Today we're looking at Leetcode 3170, Lexicographically minimum string after removing stars, which was featured in the recent weekly contest 400. So this question reads that we are given a string s and it may contain any number of star characters. And we want to remove all of those star characters. So when we do run into a star, what we want to do is we want to remove it, and we also want to remove the smallest non-star character that has appeared to the left of it. And if there are several of these, we can delete any of them. What we want to do is return the lexicographically smallest resulting string after removing all star characters. So let's look here. We'll see we're given AABA star, and the output we're given is AAB because we remove the star character and we also remove the smallest character to the left. And what is that character? It is A. You'll see that we actually have three options for which A to remove, but we end up removing S3 because it results in the lexicographically smallest string. So let's take a closer look at this example and see exactly why we choose that character to remove. So as we said before, when we see a star, we want to remove the smallest character that appears to the left. And here the smallest character that appears is A. So we actually have three options for which A we can remove. And let's look at all those options. If we remove this first A, what we end up with is A, B, A. If we remove the second one, we also end up with A, B, A. But removing the third gives us A, B. And this is the option that is lexicographically the smallest. So for lexicographically smallest, what we want to do is prioritize having smaller characters as far to the left as possible. You can think about why. So say if we had A, and then we had A, B, B, this prefix here, this AA prefix, this will by default be smaller than anything that could possibly come with this AB prefix, because just by having this character here, it automatically disqualifies this and any string that comes after from being smaller than this. So ideally, we want to preserve these small characters to the left as much as possible. So what we can instead do, and what we actually do in this case, is we find the rightmost occurrence of that smallest character, and we're going to remove that. So essentially what we can do as we go through is keep track of all the characters and where they appear. So let's look at what that would look like for this example. So what we can do is keep a hash map of characters and where they occur. So let's go through. So we see A first appears at index 0. We go to the second character, it appears again at index 1, and then we see B appears at index 2, and then another A at index 3. But then we get to our star. So we get to the star, what do? We know that we have to remove the smallest character that has occurred at this point so far. So here, our keys are the characters that have occurred, right? So we can go through all of these keys in order, starting from A and going to Z, until we find one that has occurrences. What do we do at this case? Well, we said when we find the smallest character, we want to remove the one that occurs as far right as possible, because this is how we can preserve the lexicographical ordering of the string. So we see here, the one that appears the most to the right is this index 3. So this tells us that we want to remove this A, which, as you remember, gives us AAB, which is our answer. So essentially what we're going to do is go through the string. We're going to keep track of all the indices where the characters occur, and when we hit a star, we could find the smallest character and remove the last occurrence of it. And this is going to take O of n time. So you might be asking, well, aren't we going through these keys every time that we hit a star? There could be many stars. Well, this is true, but remember, in the worst case, we have 26 keys. So even if we had to go through a ton of stars, say O of n stars, we'd only have to go through 26 keys each time. And we know that with big O analysis, we remove any constants. So this cancels out and just leaves us with an O of n times complexity. So let's actually go over to the code and see exactly how this is going to work. So here, the first thing that we do is declare this hash map. And what this is going to do is it's going to store each character as a key and then a list of all of the indices where that character occurs. We're also going to have this removed indices, which is a set which keeps track of the indices of characters that we've removed from our final string. So now what we do is we iterate through this string s. So if we see this star character, what we're going to do is we're going to iterate through all those keys like we said before. And now if we ever see a key that has occurrences, we're going to just pick this one. And why do we do this? Because we're going through those keys in order. So we're starting with A and ending at Z. So we're guaranteed to, whenever we hit this condition, that it will be the smallest character that is currently has occurrences. So when we do hit this, we're just going to remove that last index from those indices that we've seen and add it to our removed indices. And this lets us know that in our final string, this index is going to be removed. So then what we do is we just break at this point, because like we said, we found the smallest one. There's no reason to continue. And then if the character that we've seen is not a star, we just add its index into that hash map so we can use it for later. Then once we do this, we actually rebuild that string. So we start with an empty string here, and then what we do is we're going to iterate over all of the characters in S again. So if the character is a star or the index is one that we have removed, we just continue because we do not want it in our final string. Otherwise, we append that character onto our new string. So then at the end, we're just going to submit that new string. So let's submit and make sure that this works. And it does. So this is a pretty interesting problem, one where you have to remember that iterating through an alphabet is a very limited kind of operation. So it's something that we can do and still preserve our O of n time complexity. So hopefully this is helpful, and thank you for watching.